Hello. Today I'm going to be explaining how this circuit implementation from Milestone 2 works. Uh, this whole milestone is more or less just the control units, so I'll just explain those. Um, let's start by asking ourselves what we need the circuit to do. We want it to do the following operations: the fetch, decode, and then some memory reference operations, and then one register reference operation. So let's just start by the fetch operation, for example. So here in the control units, we have a counter that goes into a decoder that is used to denote the time signals, and here we have a decoder connected to the instruction register that takes the first 3 bits after the most significant bit, so these 3 right here, and from that we choose which operation we're going to be doing, but that still has to decode. So let's just go to the time signal. So now, for example, we're at time 0, t0. This is t0. So at t0, we need to move whatever content is in the PC to the AR. So we need to set the AR load to 1, and we need to put the PC onto the bus. So we need to set the select lines to the select lines that would choose the bus, and set the AR load to 1. So this is what happens. So given that T0 is active, all we really need to do is just connect it to an OR that tells it just takes another operation thing. Just it's connected to an OR that results in the AR load being set to 1, and it's also it's also taken to the select lines encoder, which just chooses which register it's going to choose, which is 101, because here in my implementation I chose to place the PC at input number 5. So that's how that works. The reason why there's an OR gate here, and you'll find a lot of them all around, is because sometimes more than one instruction can need the same output. So for simplicity, we just OR all of the operations that need, for example, the AR load to be set to 1, or the PC increment. Like, for example, the PC increment, which comes up, I think it's the next one, T1. You'll find it here, the PC increment. So all we really need for T1 for this to happen is for the time signal to be T1. So if this is T1, like this is now T1. Just take the active wire and connect it to something called the IR load, which is what we need. We need to read the memory, put it on the bus, and then put the memory at this address into the IR register, IR, and so load it with 1, and increment the PC. So to increment the PC, it's pretty easy. It's a counter. Because the milestone description said so, and the counter has a input that just, if it's a 1, it just increments it by 1. So all we really need to do is just have an output that's just PC increment 1, and it's connected to an OR gate because there's another operation that needs to increment the PC, which I'll get to in a second. But let's just look how the rest of T0. T0 is also connected to an OR gate that activates the memory read, and it's also connected to this encoder that produces 100, which is the location of our memory. So now, as you can see, we're reading memory, we're putting it on the bus, we're loading it into IR, and then we're incrementing PC. Now I'll get back to this in a second. Now we're going to decode so we can find out which operations we are doing. There's AND, load, add, STA, I don't know what it stands for, bun, sub, and SZA. 1, 2, 3, and 4 of these are using the what's it called, ALU unit, ALU, and 2 of these are just normal, like something else different. So what we need to do here is check, depending on this thing. We take the first 3 bits after the most significant bit and put them in a decoder and choose whether, and depending, I mean, on the output of this decoder, and ended with the time signal T4 or T5, depending on which one. It does something. So let's, for example, oh wait, before I forget, at T2 we also need to load the IR, the last 12 bits of IR into the address register, but in this specific implementation, because the memory is so small, it doesn't need 12 lines, it needs 6. So it's 0 to 5, the first 5 bits from the right to AR. So at T3, all that happens is that the address is carried out. I'll explain this in a second. AR is loaded, and there's something called an address multiplexer, which is set to 1, which is just something that we implemented in Freudian slip that we implemented in the main circuit, which is a multiplexer that is right behind the input of AR, which is just to say that if this is set to 1, take this address. If it's set to 0, take the addresses that are given to you by the bus. That's how that works. Now we just decode. Now, for example, I'll just explain like 2 of these. So, for example, D0 T4, it's ending. So, for example, for D0 to be so if we can have D0, that means that these bits are 0, which is the case. So let's just wait until we reach T4. T3 nothing happens because there's no indirect referencing. So D0 T4 is active because D0 is active and T4 is active, so both of them ended together active. What we need to happen at D0 T4 is for the memory at the address to be moved into DR. So the DR load is 1. The memory read is active, and the bus is carrying the memory. So as you can see here, this is connected to an OR gate with all of the possible commands that require the DR load to be active, and so it's an OR. So if one of them is active, all of them are active. It doesn't matter as long as there's one of them active. So there's a 1 over here. So the DR load is 1, and also the memory read is 1 because that's what we need. And the select lines are set to 4, which is where the memory is in the solution of milestone 1. So that's how that works. Let's go to the next operation, D0 T5. We just move 1 more here, D0 T5. D0 T5 ended together, 1, 1 is 1. Now we take this and we go to the ALU and go to number 3, which is 0, 1, 2, 3. Why is this 3? Because in the solution of the ALU, you can find that for the ending to be chosen from the ALU designed here, this needs to be set to 3 because 0, 1, 2, and 3. This is 3, which is the 4th input. So this needs to be 0, 1, 1, which is exactly the case. It's 0, 1, 1. Also, the AC load is 1 because we're loading something into the AC. And this here is done. This is supposed to reset the counter, which we do our time inputs with, time signals with. But the problem with this, with the naive implementation of this, is that if you just connect this to the counter, it automatically resets it. So we put it in a flip-flop, so it waits until all of this is done, and then it flips the CS to SC to 0. So I'm going to do another. So this is how you do AND. It's the same exact thing at add, load, and sub. The only difference is the ALU input is different. Though this one's for plus, this one's for minus, this one's for load. So I'm going to, for example, do this one now, because this one, there's a very specific case. In the normal case, you just automatically put the AR into PC, but for some reason, here you can't just load something into the PC. It has to be 0 first. So I just wrote it so that if it's bun, D4T4 sets it to 0, which is an option we have in the which is an option we have in the PC counter. You just set it to 0, and once it's set to 0, then we can load something into it. So at D4T4, you set it to 0, and at D4T5, you set the load of PC to 1, and you make the bus carry AR, and then you set SC. It's more or less the same as all of them. You do one, you do them all. I'll do the final one here, which is this one's a little bit different. This one increments PC if AC equals 0. Now, how do we check if AC is equal to 0? So we just get it as an input, put it into a splitter, and then split it to 1 bit, so it's 16-bit, like split it 16 times, so it's 1 bit each, and then OR them. The ORing of all of the bits individually means that if any of the bits is 1, the ORing would be 1, which means that if I negate the output of this OR right here, if it's a 1 and it's negated, it means that none of them are 1. If a single one of them is 1, it no longer is a 0, so it's no longer active. So let's just see how this works. It's D7 T3, but I did it T4. Doesn't really matter. So if we set this to 1 1 1, which is D7, D7 is active, and T0 1 2 3 4 5. I did T5. Still doesn't matter. Wait, I did do it to T4 something after that. Okay, here you see it at T4. T4 ended with D7, ended with the fact that it's all zeros. Just ORed with, I told you I'd get back to it, ORed with this thing, which is just the increment from here. So again, because I said sometimes there are more than one operations that need the same output, so you just OR them together. So, and if any of them's a 1, it's a 1, whatever. So D7 ended with T4, ended with the fact that they're all zeros, just increment the PC. That's how that works. It's connected to the main. It's all labeled. So all you really need to do is just connect the address lines to the multiplexer, connect the address multiplexer to the enable, to like the select lines of the multiplexer, memory read to memory read, DR load to DR load. So it's all pretty straightforward. I don't really think I need to explain this part. AC is connected to AC and IR is connected to IR. We test this code by adding a program, which I pre-wrote. Well, not pre-wrote, I just took it from the Milestone, and then just run it by running the clock. As you can see, it's taking 2, putting it in the DR, then loading it into AC, then taking the DR to be set to 5, then we just add them, and so on. So that's how that works. Thank you.